Hey, Bill here. Today I'm going to show you my LED controller emulator. So let's have a look at it. You've seen the LED controller. I've shown you many times that I've put together, driven by this microcontroller down in here amongst all those wires. And I've told you that I wanted to have it so that it's up on the wall and I can send text to it from any application, or perhaps you could send text to it if you wanted through the internet. And in order to do that, I wanted to use a Wi-Fi module because I didn't want to run wires up to that, up to the wall there. So using one of these Wi-Fi modules, just a little square here, not that whole bit, just that little piece is the microcontroller, or well, it's the microcontroller system on a chip. I want to drive that display. Now, not a big deal. In the process of doing it, though, just making mistakes, I burned out a couple of those displays. And now they're not expensive, but you have to wait 4 weeks to get them from China. And so I decided that I ordered some new ones, but in the interest of not damaging any more, that I would build an emulator that would pretend to be those displays so that I could fry this other cheap piece of hardware that I've got plenty of instead of those displays. So let's have a look at that. And what I've done is I've taken that Wi-Fi controller and programmed it as if I was talking to the controllers in that LED display. But I have connected it through this to this microcontroller here. Now this microcontroller here is programmed to understand that, and also to send that data out through the USB to the PC, which is connected to what's called a virtual box running Linux. And then I program on that Linux box that I've written that allows me to display pixel data. So let's zoom in on that guy. You'll see these pixels that I've clicked on. I'm going to bring my mouse up here to show you that. You click on these different boxes and you can turn them on or off. You have to click through several times to change the shading of it, and then eventually it's off. So, but for this purpose of this display test, this is segmented to just the top 8 bits are being refreshed. That's why these ones are staying on the screen, just as a demonstration. Sorry about the jumping around. Let's quit that application and start it back up. And, oh, you can't do that while it's running. Sorry. Restart everything. Okay, so that's up and running. And our display should come up here saying "Be built is cool" momentarily. Right about, there we go, starting to scroll in. Yeah, so that's how that guy works. What I did was, as I said, I originally built this to be an editor, for a bitmap editor, and that's what I use it for. But I decided, hey, with a couple of modifications, I could have it so that I can write data to it from another application. And so that's exactly what we've done here. And so the emulator is writing to this display and refreshing this whole display. Every time you see that tick over 1, it's refreshing the entire display to do that. It's rewriting that text each time, which is exactly the same process that goes on over here. Now it's going on a little faster here, and that's because I've got this thing throttled down to talk to this display, because pardon me, the microcontroller that's doing the interfacing is running at 16 megahertz as opposed to this chip, which is running at 160 megahertz. So it can't keep up. As you can see by this almost solid communication light here, he's busy full time just reading data from this guy and writing it out to that display. So if you think about it this way, this microcontroller is talking directly to that display and putting that data up on the display. That's one transaction. He just writes that data and it goes straight there and up on the display. Here, he's writing all the data. This guy has to absorb all the data until he's got a full packet. He can't do it bit by bit because there's information in there that he needs. He can't do it until he's got the full packet. He reads that data and then pumps it out as fast as he can in the new format, which is completely different in this application. So it's actually quite remarkable he's able to do it at all. Now, the beautiful thing is that the way that this was put together, I can take these 5 wires and unplug them and connect them here and drive this controller without making any changes to this device. It does not know that it's talking to this microcontroller or whether it's talking to that display. It just uses the same mechanism, and that's how this becomes, can be rightfully called an emulator, because it's pretending to be that hardware. What else can we say about this? Oh, we've already typed in here Toronto Maple Leafs on my Hive control. Now this is just a web page on my server Turtle. If I click send on here, it's going to send it via Wi-Fi to this module, who's then going to send it to that device, who's then going to display it on the screen. There we go, Toronto Maple Leafs. And it was scrolling off the screen when I did that. Not a very good demo, I'm sorry, but who cares that much? It's already up to 6.5 minutes, so let's kind of bring this to a close. Just want to show you that it's actually working, doing what I said it would do. And now the beautiful thing about this is now I won't damage any more displays, and I can carry on. The silly part about it is that, well, I've already written the software, haven't I? So it's just really a matter of tomorrow I'll be plugging this into the new displays and verifying that it all works, but there's no reason why it wouldn't at this point. And so, in conclusion, that was super fun, but it was really hard. Oh, that was one more thing. The way that this is done is that data is written out using a protocol called SPI, which is Serial Peripheral Interface. Most microcontrollers have it built in, and this one's talking directly using SPI to this device. This one has SPI, but it's not, in my opinion, industry standard. It's one of those standards in the industry that is not well defined, but there is a de facto standard that everybody follows, and they're not following it. They've expanded on it, and it's not as good. And because I had to throttle down to talk to this device, I couldn't use the built-in SPI because you couldn't throttle it down. It runs at a certain speed and it ain't going any slower. So that means I had to write my own, what's called bit banging. Instead of using the built-in SPI, I used the general purpose I/O ports to take each individual line and drive it myself and emulate the protocol. So this is kind of like a double emulation going on here. In any case, just a quick story about that. The two main parts of the serial peripheral interface are what's called a system clock, which is just a signal that goes on and off at a set speed. And then you have your data line. And now this is a one-way communication. You also have a data line that comes in, and then you have another control line called the CS line. We only need to worry about these two right here. The others are not important for this conversation. So the way it works is you send out a clock that goes high and it goes low, and it goes high and it goes low. That's a clock. The microcontroller is set to that you can read the state of this line when this one is going to a high, transitioning to high. Then you read the state of that line. Now you've got a 1 because that's high. And the next transition to high, you read this line, you've got a 0. The next transition to high, you read a line, you've got a 1. And that's how a clock and a data line work together. This is really typical of many electronic protocols. In this particular case, SPI was one of the earliest that puts this together. So all I had to do was actually, it's pretty complicated because you have to get the timing just right. I had to write out the state of this line to represent the bits of the data that I am trying to transmit. At the same time, generating a clock signal on another line that will allow the remote host to read that data, know when to read the state of that line. And the reason that's important is, if you can imagine, if you're sending the string, I should have different lighting for this. If you were sending the string, let's go up here, 1 0 1 1 1 1 1 1, that would look like this: 1 0, and then a bunch of ones. And it doesn't go up and down for those ones, it just stays high. So the remote end, how's it going to know when to read that line? It knows because of the clock. And the clock signal, which is slightly offset from the data, would be going like this all the way along. And I'm not doing that right because I've represented only 1, 2, 3, 4 bits with these leading edges. That's where it's going from low to high. Low to high. Just highlight it. Low to high. Low to high. That's called the leading edge. And it's when the leading edge occurs that the remote host is going to read the data line. So he reads a 1. No, he's going to read a 1 because, well, I screwed this up. He's going to read a 1, and then he's going to read a 1. So all he's going to have seen is 1, 1, 1, 1 when I was trying to send this data. So you can see how critical it is to have that clock just right, pacing the data as you're sending, or in this case, you're not sending, you're just leaving it high. So that's the job of the programmer, called bit banging in a microcontroller, to drive that data line. I don't know if I explained why I'm doing that in the first place. Oh, yeah, it was because it was non-standard. But in any event, very challenging, a lot of fun. It all works. I'm done. Thanks for watching.